Hi, everyone. My name is Emily Allen, and I'm here with COVE, the Center for Ocean Ventures and Entrepreneurship, which is an innovation hub for over 60 different marine technology companies in Dartmouth, Nova Scotia. And today I'll be talking to you about exploring the digital ocean, how scientists collect and use data to better understand what goes on beneath the waves. So before we get into the cool technology, I'd first like to talk about why we're interested in studying the oceans. So the oceans play a critical role in supporting life on our planet. The ocean produces over 50% of the world's oxygen, so you can thank the ocean for every second breath that you take. The ocean also helps regulate our climate and weather patterns, stores 50 times more carbon dioxide than our atmosphere. So it's really helping play a role in the way that our planet is dealing with climate change. It's, of course, an important source of food, an important source of medicinal products, and the main form of transportation of goods on a global scale. So from the technology in our pockets to the clothes that we wear. And so apart from all of these things that benefit us as humans, things live there. So the ocean is a really incredible source of biodiversity, with new species being discovered every year, and each play a really important role in the ocean ecosystem. So it's important that we help maintain that biodiversity. All of this to say that the ocean is important because it helps us understand how we are affecting and also being affected by changes in the Earth's environment. So how do we study our oceans? Today, I'll introduce you to some cool tech that collects data and helps researchers better understand our oceans. So the first cool piece of technology that I'll be talking about, which has greatly impacted the way we collect ocean data, are underwater gliders. So underwater gliders are a type of autonomous underwater vehicle, or AUV, and they help collect data autonomously, which means that these gliders are designed and engineered to operate themselves and perform tasks without any human intervention. So they can be fitted with many different types of sensors and samplers, and they're pre-programmed for specific missions. So they have the ability to gather information about their surrounding environment, to make decisions, and because they can continuously receive new instructions remotely from operators through satellites, glider missions are incredibly dynamic and flexible. So in the past, research vessels crewed with personnel would have to travel to very remote locations and deploy instruments or send divers in the water to collect data. So as you can imagine, this is really expensive and time-consuming, and only allows for data collection when researchers were physically at their location of interest. So this would require voyages lasting months at a time to collect large amounts of data. So the development of these gliders has allowed researchers to collect data sets that span over periods of weeks to months and thousands of kilometers, all while allowing researchers to stay ashore and view the data that's transmitted remotely through satellite systems without even leaving their desk, which is pretty cool. So gliders are fitted with specific parts which enable them to do their job. So they have an altimeter there at the front of the glider, which is used to measure the altitude or the height of the glider above the sea floor to track how deep it's traveling. It has battery packs, which keep the sensors and communication systems alive. It has an antenna used to send and receive information. And they also have a buoyancy engine and air bladder, much like fish do, to help them move through the ocean. So gliders move through the water by regulating their buoyancy. You may have heard this term before, but I'll just quickly explain it. So an object's buoyancy is its ability to float in a liquid, and it depends on the density of that object, in this case, the glider, relative to the density of the liquid, in this case, seawater. So to dive below the surface, gliders need to decrease their buoyancy or decrease their ability to float by increasing their density to that of above seawater. So to do so, gliders will pump seawater into the main body of the vessel, decreasing its density by ridding the glider of air and causing it to sink. And so once the glider reaches its maximum depth, it begins to pump water out of the vessel, decreasing its density and causing the object to float back up to the surface. So gliders also have weights near the front of the vessel that help angle the nose up or down in time with this process, which causes the glider's forward motion through the ocean. So the durability and flexibility of these gliders means that researchers can easily and safely collect data from new and challenging areas, such as shallow waters that aren't reachable by boat, to extreme depths of up to 1 kilometer below the surface of the ocean. So what kinds of technologies can we put on gliders? One common instrument deployed on floating buoys or gliders are hydrophones, which are used for listening to sound underwater. So you can think of a hydrophone as like an underwater microphone. So when something makes a sound, it releases energy in the form of a vibration. And so these vibrations, or small back and forth movements, cause all the molecules around them to start moving as well, kind of like a ripple effect. And so these molecules bump into each other and they send energy through space in what we normally refer to as a sound wave. So molecules are much closer to each other in liquid than in gas. So the time it takes for all of these molecules to bump into one another and transmit sound energy is much shorter underwater than compared to in air. So on average, sound travels about 4 times faster in water than it does in air. And so because of this, standard microphone technology doesn't actually provide accurate documentation of underwater sounds. And so that's why we use hydrophones, which are specifically designed for detecting sound underwater. So most hydrophones are made from specific material, which is normally some sort of crystal or ceramic. And so when a sound wave is traveling underwater, the movement of the water molecules result in a pressure change around the device, which you can see there in the diagram. So when exposed to changes in pressure, this specialized material releases small electrical charges. And it's actually these small electrical charges that are recorded as sound data. And this data can be analyzed by experienced personnel to make predictions about and identify the types of ocean sound captured by the hydrophone. So how do we view sound data? So here we have some hydrophone data, and it's definitely tricky to wrap your head around the concept of seeing sound. So I'll walk you through what this figure is telling us. So on the x-axis there, we have date and time. You can see this data was collected on November 1st, 2016. On the y-axis, we have frequency, or how we measure sound. So the frequency equals the total number of sound waves produced in 1 second. And the units for frequency are called hertz. So if we have, for example, if we have 5 complete sound waves produced in 1 second, the frequency is 5 hertz. So the higher the frequency, the higher the pitch of the sound that we hear. So you can see here that dolphins are much higher pitched than, say, an earthquake. And the warmer colors in the figure, so the reds, represent more sound energy or louder sound at a given time and frequency. And so skilled researchers can listen to hydrophone recordings and look at this sound data to determine what noises are being picked up, and they can monitor underwater sounds. And so this has applications in a ton of different fields of the marine sector. So hydrophones can be used in surveillance and defense, such as listening for different types of ocean vehicles like submarines. They can be used in monitoring for earthquakes and other large-scale events. We can use hydrophones to learn more about noise pollution and the effect that can have on ocean life. And hydrophones can be used in research and conservation of many ocean species. Which brings us to our first of two case studies that we'll be looking at today. This one highlights the use of hydrophones in species conservation. So you may have heard of the North Atlantic right whale, which is one of the world's most endangered large whale species. So the latest estimates suggest that there are fewer than 350 individuals remaining in the world's oceans. So by the early 1890s, commercial whalers had hunted North Atlantic right whales to the brink of extinction. And these whales actually got their name from being the right whale to hunt. So whaling is no longer a threat, of course, but this species has never recovered to pre-whaling numbers, and human interactions still present the greatest danger to this species. So things like entanglement in fishing gear and vessel strikes are the leading cause of North Atlantic right whale mortality. As well, increasing ocean noise levels from human activities are also a concern, since this noise may interfere with right whale communication and increase their stress levels. And so recently, conservation scientists and the government have worked together to use hydrophones to detect the presence of endangered right whales in offshore regions, many of which are in and around Canada. So using a system of floating buoys and gliders in the Gulf of the St. Lawrence, scientists have outfitted these platforms with hydrophones specifically to detect the calls of right whales and transmit this data to a network of marine mammal experts for confirmation. So if the sounds are confirmed by scientists to be that of right whales, a system of protocols can go into place for marine activity in the area. So things like the prohibition of fishing, mandated slower boat speeds, or in some cases, they might close the waterway altogether if they know that right whales are hanging out in the area. So now it's time for you to explore some real data. So you're going to be given the link to this interactive website. You can see that there are many settings that we can change to choose the data that we're interested in. And so because we're interested in hydrophone data, you can go to the sampling method tab and select Viking buoys. You can use the period tab to change the dates of the data that you'd like to view. And when you click on one of those colored squares, you'll actually see real data pop up on the screen. So what I'm going to do is I'm going to give you a few minutes to explore this real hydrophone data. And I've included a few questions here to guide your exploration and get you thinking about the information that you're seeing. So feel free to pause the video now and go and check out this real data and come back once you've done some exploring. All right, moving on. So now we'll move on to our next cool piece of technology that we can put on gliders. So one of the most common oceanographic instruments is the conductivity, temperature, and depth sensor. We shorten this to CTD sensor as it's quite a mouthful. So this instrument helps provide data about the basic physical properties of seawater that inform researchers' thinking. So the sensor measures the water's conductivity, or the ability of a solution to pass an electrical current. And it measures the conductivity in order to help calculate the water's salinity, or the concentration of salt in the water. So when salt is dissolved in water, it breaks down into two charged particles, one negative and one positive. So the presence of these charged particles allow electric current to move through the water. So this means that the more salt in the water, the more charged particles. meaning the higher the conductivity of a solution, the higher the salinity. So as you can predict, seawater has a high conductivity and salinity. Salinity is often measured in parts per thousand. And so to give you an idea, the salinity of seawater is roughly 35 parts per thousand compared to that of drinking water, which is around 0.1 parts per thousand. The CTD sensor also measures temperature of the water, which, as we know, can vary greatly throughout different geographical locations and depths within the ocean. And lastly, the sensor measures depth. So the combination of conductivity, temperature, and depth measurements provide a pretty basic but comprehensive understanding of the water's physical properties at a given location. So why do we care about these parameters? Well, generally, specific areas of the ocean hold specific properties and patterns. And so when the properties or patterns of a particular area don't match the patterns we would expect to see, scientists can then investigate the area to determine what might be causing these anomalies or changes in the ocean. So CTDs on gliders have the ability to take measurements throughout the entire water column, meaning the surface to the seafloor. And many ocean patterns observed involve relating depth to variables like temperature and salinity. So one pattern that we typically observe is a decrease in ocean temperature as depth increases, which you can see in the graph there on the left. So with energy from the sun that warms the water can't reach past a certain point, this is when the water starts getting cooler. And so you've most likely heard of this before or even experienced this firsthand. If you've ever been swimming in a lake or an ocean, when you wade out or dive down deep and experience those colder temperatures beneath the warmer surface waters. So salinity also tends to change as well with depth. And the relationship between salinity and depth is determined by multiple conditions of the area that scientists are studying. So, for example, in warm areas that don't receive much rain, salinity is generally higher near the surface of the water because water molecules evaporate much easier and are not quickly replaced, meaning that the ratio of salt molecules to water molecules is much higher near the surface. But in colder regions, like the Arctic, low evaporation and freshwater glacier melt decrease the salinity near the surface and increase the salinity. And so the salinity is increased near the ocean floor. You can see that comparing the polar and warmer regions there in the graph on the right. So you can see why it's important for CTD sensors to measure depth, as it provides a context for temperature and salinity readings, which vary with depth and help us compare patterns that we're observing to the ones that we expect to see in the ocean. So what kinds of changes are CTD sensors looking for, and what can they tell us about the ocean? So this brings us to our second case study. So CTDs have been deployed on gliders to monitor and predict weather events across the globe. So this case study focuses on the use of CTD sensors to track hurricanes in the Atlantic Ocean. So a bit of background about hurricanes. So the path and intensity of Atlantic Ocean hurricanes are linked to both atmospheric and ocean conditions. So during the past 20 years, improvements of hurricane intensity forecasts, or what we know as categories of hurricanes, and in particular, when these hurricanes intensify rapidly, have lagged behind those of hurricane track forecasts. So in short, we've gotten pretty good at predicting the path of a hurricane. But we have some work to do in predicting the intensity or the category of the hurricane as it hits land. So as you can imagine, this information is really important for decision making when it comes to the way that we prepare for storms. So in general, hurricanes have the potential to intensify when a suite of ocean conditions are present. So studies have shown that the correct monitoring of ocean temperature and salinity in the upper 100 meters of the ocean actually improve hurricane intensity forecasts. So heat is one of the main engines that drive tropical storms. So warmer oceans create conditions for storm intensification because as the storm travels across the warmer ocean waters, they're able to pull in more water vapor and heat. So this means stronger winds, heavier rainfall, and more flooding when storms hit land. Also, salinity in the upper portion of the water column can be an indicator that the upwelling of cooler water from the depths of the ocean that normally happens during big storms isn't occurring, meaning that warmer sea surface temperatures exist and fuel these storms. So monitoring salinity is important for understanding hurricane intensification as well. So the correct monitoring and representation of these ocean features measured by CTD sensors is really key to improving hurricane intensification forecasts. So for many years, scientists had little concrete data about how the ocean conditions can affect the development of storms like hurricanes. And so now the Atlantic Oceanographic and Meteorological Laboratory has launched a hurricane glider project. So what they're doing is they're using a fleet of gliders to take real-time data collected during hurricanes and implement it into their prediction models to create more accurate forecasts surrounding hurricane path and intensification tracking. So overall, the use of gliders is greatly improving scientists' ability to track and analyze tropical storms, and in the process, this can actually help save lives by informing decisions like evacuations of specific areas during approaching storms. So again, you'll be provided with the link to this interactive website to look at real glider data in the Atlantic Ocean that's being used to track hurricanes. So under the field observations, there you can see you'll see on the left-hand side, you'll want to select gliders. And then you'll see purple lines that track the glider missions. So when you click on a part of a purple line, a figure will be generated displaying CTD data that you can see here in this slide. So again, I've included a few questions here to help guide your exploration of this real ocean data and get you thinking about the information that you're seeing. So take some time to pause this video and explore this real CTD data collected from gliders in the Atlantic Ocean. And next time you see news of a tropical hurricane or storm brewing in the Atlantic Ocean, you can actually pop on this website and view the ocean data in real time and make your own predictions about the storm. So take this time, pause the video, and then we'll move on to the next part of our talk. So now I'd like to talk about what's next for the ocean sector. So the ocean sector is growing rapidly, and with that comes some challenges and, of course, some unique opportunities. So you can see that advances in technology have vastly increased the amount of time and space over which we can collect data. So if you think about a glider sent on a 4-month mission that has a CTD sensor collecting data every second, that's about 30 million data points. So there are so many different types of instruments collecting data on a variety of platforms over very long periods of time, all producing unprecedented amounts of data. So this is great news, but it of course comes with challenges in the way that we store, compute, and analyze this big data. So this is a hot topic right now in the ocean sector. Of course, there's the improvement of current technology and the creation of new technology. So a few examples of ongoing exploration are things like improving programming used in autonomous technologies, the use of AI in ocean technology, and increasing the life of batteries used in technologies like gliders to allow for longer and farther missions. So a lot of the tech used in the marine industry is constantly being developed and improved, as well as new technology being developed. So it's a pretty interesting sector and pretty exciting sector to be in. The last thing is filling careers in the ocean sector. So we really need people. We really need young people because the sector is growing so rapidly. The marine sector is this incredible environment whose success really depends on multidisciplinary collaboration from people with a diverse set of backgrounds and knowledges and skill sets. So meaning people with a huge range of expertise and talents are coming together to play a crucial role in the success of this sector. So from careers like biology, chemistry, physics, to geology, to engineering, to IT, to computer science, to education, to business-oriented talent, to vessel operators and skilled trades. And the list goes on and on. But the marine sector is really excited and it's growing really rapidly. And so we need young people to help grow and innovate and bring new ideas to the sector. So with that, I'd like to say thank you very much for listening to this talk on exploring the digital ocean. I've left my email here if you have any questions for me. And I'm also going to give you your gamification code. So here's your gamification code. I'm going to hold it up here. This is the code for this session. Just make sure to input it to receive your gamification points. And thank you so much for taking the time to watch this talk.